Last time, we left you with a problem. One neuron can only draw a straight line. So how does this ever learn a curve? Watch this. 4 dots. 2 yellow, 2 blue, at the corners of a square. Your job is simple. Draw one straight line that puts the yellow on one side and the blue on the other. Go ahead, tilt it any way you like. It will never work. Not because you are bad at this, because it is impossible. But stay with me, because by the end of this video, you will watch this exact square get folded until those 4 dots fall onto opposite sides of one clean cut. And the block that does the folding lives inside every layer of GPT. Look closer. The 2 yellow dots sit on opposite corners, so do the 2 blue. Any straight line you draw, no matter the angle, always leaves one wrong color stranded on the wrong side. This little 4-dot puzzle has a name. It is called XOR. And a single neuron, which is nothing but one straight line, cannot solve it. That sounds like a footnote. It was not. This exact puzzle froze artificial intelligence research for the better part of a decade. And here is what you will actually walk away with. You will understand exactly what a hidden layer is, and the one tiny trick that gives it almost unlimited power, the trick that does that folding. The thing you are about to build is not a toy. That block inside every layer of GPT, you are starting to build a piece of it right now. Quick refresher, because everything hangs on it. A single neuron takes your input, multiplies it by a weight, adds a bias, and that is it. Just W times X plus B. Geometrically, that is the equation of a line. So the only thing one neuron can ever do is carve your space with one straight cut. Everything on one side, it says yes. Everything on the other side, no. One neuron, one line. Hold that picture. We are about to break it. Back in 1969, 2 researchers, Minsky and Papert, proved this on paper. A single layer of these neurons, they showed, simply cannot compute XOR. One straight line is not enough, and the math said so cleanly. The effect was brutal. Funding dried up, optimism collapsed. People walked away from neural networks for years. The field went into what we now call an AI winter. A 4-dot puzzle a child could solve in their head had stalled an entire science. So what broke the deadlock? Not a smarter neuron, more of them. Here's the first move. Instead of asking one neuron to do the whole job, we line up several of them side by side, all reading the very same input at the same time. Watch the input fan out. It does not flow through them in a chain. It splits and feeds every neuron in the row at once. Each one is still just its own straight line, asking its own little question about the input. But now, instead of a single answer, we get a whole row of answers, a list of numbers. This row of parallel neurons is what we call a hidden layer. We can write the whole layer in one breath. Each neuron has its own weights, so we just stack them. One row of the grid per neuron. That grid of weights gets a name, a matrix, written as a capital W. Multiply your input by W, add the biases, and out pops the entire row of answers at once. Do not let the word matrix scare you. It is bookkeeping. It is just all of those individual neuron lines, written down in one tidy table. The layer is the table, nothing more. But here is the catch, and it is a big one. If every neuron is just a straight line, then a whole row of straight lines added back together is still a straight line. Stack 1,000 of them, still a line. We have more neurons, more weights, more numbers flying around, and somehow exactly the same power as before. The square is still unfoldable. So more neurons on their own bought us nothing. Something is missing, and it is almost embarrassingly small. Here it is, the whole secret. After each neuron computes its straight line, we pass that number through one tiny rule. If it is positive, let it through unchanged. If it is negative, clamp it flat to 0. That is the entire rule. Keep it if it is positive, otherwise 0. It even has a clunky name, ReLU, but ignore the name and watch the shape. We take a perfectly straight line, and at the point where it crosses 0, it suddenly bends. A straight line with one kink in it. That kink is everything. The whole rest of this video is what happens when you start adding kinks together. Think of that kink as a fold. A single neuron with its kink is one straight crease in a flat sheet of paper. It can fold the paper exactly once along one line. Before the crease, smooth and flat. After it, the surface tilts the other way. One neuron, one crease, one fold. On its own, that is not very impressive. But this is the brick. And once you have the brick, the only question left is what you can build by stacking creases on top of creases. So let us add a second neuron, a second crease bending the other way in a different spot. Now feed both into the next layer, which simply adds their answers together. Watch what happens. One kink going up, one kink coming down, and where they meet, the line lifts into a little bump, a tent. We did not draw a curve. We added two straight, kinked lines, and a shape that bends in the middle just appeared, for free. Two neurons, two creases, and already we have left the world of straight lines behind. Now do not stop at two. Add a third crease, a fourth, a fifth. Each new neuron drops one more kink wherever the network wants it, at whatever angle it likes. And as those kinks pile up, the line starts to wave. It rises, it dips, it wiggles. From a distance, it looks like a smooth, flowing curve. Get up close, though, and you will catch the honest truth. There is no curve. It is dozens of tiny straight segments, joined at the kinks, faking a curve so well your eye is fooled. More neurons just means more creases, which means more bends, which means more complex shapes you can carve. Sit with that for a second, because it is one of the most beautiful and least known facts in all of AI. Every curve a network like this ever draws is a lie, a gorgeous, useful lie. Underneath, it is always just a fan of perfectly straight lines, bent at the kinks and stitched together. The fancy term is piecewise linear, and you have earned it. The curve is the shadow. The creases are real. Now let us point this folding machine at the one thing a single line could never beat. This next part is the one that trips everyone up, so slow down with me. Stay with me for 60 seconds, and it will snap into place and stay there. The question is this. We have seen kinks bend a line into a curve. But how does bending a line actually let us separate those four impossible dots? How does adding folds turn the unsolvable into the trivial? Here is the way to truly see it. Stop thinking about drawing a curvier line. Start thinking about folding the floor that the dots are standing on. Picture the flat square as a sheet of rubber with the four dots sitting on it. Now bring our hidden neurons online. Each ReLU neuron presses one straight crease into the sheet and folds the whole plane along that line. One crease lifts part its floor up. A second crease folds it again, the other way. The sheet that was flat is now a folded landscape with ridges and valleys, and the dots have come along for the ride. They have not moved relative to each other. The ground beneath them moved. And here is the magic. After those two folds, watch where the dots end up. The two yellow dots, that started in opposite corners, get folded so they stack up onto the same side. The two blue ones land together on the other. The square that no straight line could ever split has been bent so that the colors are now cleanly stacked, one group high, one group low. They are no longer tangled across the diagonal, they are sorted. The fold did the work that the line could not. And now, the moment. On that folded landscape, we ask the final neuron to do the one thing a neuron is good at. Draw one straight line, just one. And because the floor is folded, that single flat cut now slices cleanly between the colors. Yellow on one side, blue on the other, done. The four-dot puzzle that froze a field for a decade, that proved a single neuron helpless, just fell to two hidden neurons and a fold. Unfold the paper back to flat, and the straight cut you made comes back looking like a curve. That curve was never magic. It was the shadow of your folds. And once you believe the fold, you cannot stop. Throw something genuinely cruel at it, a spiral. Two arms of color wound around each other that would make any straight line weep. Give the layer more neurons, so more creases, and watch the boundary curl. It folds and folds again, wrapping itself into the spiral, tracing the gap between the arms. There is a free toy where you can do exactly this in your browser, called the TensorFlow Playground. Add neurons with a slider and watch the spiral surrender in real time. I cannot recommend it enough. Now brace yourself, because here is the headline result. Back in 1989, a mathematician named Sibenko proved something that still sounds too good to be true. A network with just one hidden layer of these kinked neurons can approximate any continuous function you want. Any shape, any curve, any boundary. Not most of them, any of them. One layer of folds, in principle, can draw literally anything. It even has a grand name, the universal approximation theorem. But I owe you the honest asterisk, because this is where lazier explanations stop and quietly mislead you. That promise is an existence proof. It says such a network exists. It does not say it is small, and it does not say you could ever train it. To draw some shapes, one flat layer might need an absurd, even exponential pile of neurons. So in practice, nobody builds one giant wide layer. We stack many smaller layers instead, folding the folds. And that, quietly, is the whole reason deep learning is deep. Hold that thought. It echoes through the rest of this season. Now, you might be wondering who decides where every crease goes, where each fold sits, how steep it is, which way it bends. And the beautiful answer is nothing new. Remember the ball rolling downhill from last time? The same lost landscape, the same gradient descent, the same patient walk to the bottom. That identical loop sets every weight in every neuron, placing each fold exactly where it cuts the error down. Predict, blame, nudge. Predict, blame, nudge. We did not invent a new way to learn. We just handed the same old learner a richer shape to mold. Let us put the whole machine on one line. Take your input. Multiply by the first weight matrix, add the first bias, that is, the hidden layer. Pass it through ReLU, the kink, to make the creases. Then multiply by a second matrix and add a second bias to combine those creases into your answer. That is it. That entire expression has a name. The multilayer perceptron, or MLP. It is the workhorse block of the whole field. And you just understood every symbol in it. And now the promise I made at the start. Look at this faint shape behind the formula. That is a single layer of GPT. Every one of those layers is 2 parts. An attention block, which we will get to, and right next to it, this, the exact block you just built. Inside the machine, it is called the feed-forward network, but it is our MLP, kinks and all. So when GPT writes a sentence, somewhere in there, a stack of these folds is firing. You did not learn a warm-up topic today. You learned a load-bearing organ of the thing. So let us close the loop we opened. We started with 4 dots and 1 helpless straight line. Then 1. We stacked neurons side by side into a layer, so the input fans out to many at once. 2. We bent each one with a tiny kink, ReLU, turning every line into a crease. 3. We added the creases up, which folded the flat space until the impossible dots fell onto opposite sides of a single cut. And 4. The very same learning loop from last time places every fold for us. Line, to layer, to kink, to fold, to curve. But before you go, look back at where all of that power actually came from, not the extra neurons, not the giant matrix. All of it, every fold, every curve, the entire escape from the straight line hung on one tiny thing. That little kink, that one bend at 0. Watch what I am about to do. I am going to reach in and gently take it out. Make every neuron a plain, honest, straight line again, no bend. And the whole folded landscape, all that hard-won power, quietly collapses, layer after layer, right back down to a single, flat line. Why does pulling one tiny kink cause everything to fall apart? That is not a flaw. That is the deepest idea in this entire series, and it is exactly where we go next time, the activation.